Hello and welcome to a primer on obfuscation of Java code using ProGuard. This video is presented by Wernerware LLC. Obfuscation is a common part of many build processes, especially in Android builds using ProGuard. You can use ProGuard with any project generating zipped archives though, and it can be a good idea if you want to discourage abuse of your software. De-obfuscation can be a daunting task, but sometimes a necessary one for purposes such as digital forensics and the prospect of a challenge for its own sake. This video will show you the relationship between the everyday tasks a developer does and the process of finding meaning in the intentional mess left behind by a good obfuscator. Please see the link to the video notes in the description section below for the written version of this video along with some supporting files. Normally in a professional software project you will see obfuscation performed by the automated release build. This is more typical for JavaScript code on the front end of a web app, but it is also an integrated part of some Java applications, for example in Android builds. ProGuard is one of a number of options available for Java, and is probably the most popular because it is free. For the purposes of learning about ProGuard, it's easier to use the executable jar with a graphical interface. To start, go to the project page on SourceForge and click Download. This will give you the latest ProGuard zip. Expand this zip to a convenient location. Open up the lib folder and double-click on ProGuard GUI.jar. After any warnings you may get about executing downloaded code, you should see this screen. For the purposes of this tutorial, you should uncheck shrinking, so that you can see the effects of obfuscation on their own. Of course you will want to ensure that obfuscation is enabled. Similarly to the shrinking option, for the purposes of this demonstration you will want to disable optimization. You will need to specify the inputs and outputs. Library jars and other supporting files are included in the second section to cue the tool as to which identifiers in the code will not be touched by the process. They are external to the artifacts we are obfuscating, and therefore need to remain the same. Here we are providing the path to rt.jar again since the application did not have the correct one already. The first section is a sequence of inputs with their corresponding outputs. It's important to specify an output, otherwise the tool will process the jar and exit without recording the results. You will need to specify an actual existing file for the output, but this will be overwritten. The easiest way to accomplish this is to copy the artifact you are obfuscating with a big underscore obfuscated appended so that you can remember which is which, and believe me, when it's a manual process you will need this. You will need to click Add Input to get the unobfuscated jar onto the list. Then click on that list item so that it is highlighted. And click Add Output, selecting your copied jar for that. Finally you can go ahead and hit Process on the Process tab. This section presumes you know how to decompile Java code. If you want to learn more about that, please visit the video notes on GitHub. First, in order to demonstrate that something is actually happening when we run the obfuscator, we should decompile the artifact we had before obfuscation. I did this here in the control_out folder, as it represents the control case for our tests. Now that we have a way to refer back to the unmodified artifact, we can proceed to examine the obfuscated artifact. Just to show you an interesting hiccup that you will commonly see, let's just attempt to unzip the obfuscated jar. This shows you that the file naming conventions inside a zip folder can differ from the operating system, in my case here OS X. The obfuscator has created a lowercase c class and an uppercase c class in org/a/a/a, and the unzip command cannot reproduce this in the native file system. The same problem manifests itself when you attempt to decompile this artifact without modifiers, which is likely at least one of the reasons that Fernflower does not unzip the source for you when you invoke the tool at the command line. Thankfully Fernflower has a simple solution, the -ren, or rename argument. According to the Fernflower GitHub page, the purpose of this argument is to quote rename ambiguous, resp. obfuscated, classes and class elements unquote. We can see the effect by unzipping the results. Fernflower has taken the obfuscated class files and renamed them as it traversed the artifact in a fashion that is friendlier to the OS, so we can unzip the artifact now. They're still almost completely meaningless, but at least now they can get into the file system. So now that we have the code formatted textually once again, we can import it into an IDE and start looking for the information we need. This is where creativity can come in. For instance, a quick way to look for interesting things is to search for string literals. Generally you're going to find whatever string literals are in a given app are not changed by the obfuscation process. I found it's pretty easy to search with a simple regular expression with grep. As you can see, there are string literals in various places, but in this example mostly in the exception constructors. If you're chasing after a not exception you're getting from a dependency, this can be a great starting point, matching parts of the log output to the parameters for the exception constructor. Of course, this is not even close to guaranteed to work, but sometimes you get lucky. It may also be helpful to see which classes are used the most frequently, as figuring these out first may shed the most light on the others. Iterator seems very popular, which makes sense for commons collections, but that's a class provided by the Java runtime. We are more curious about the ones like org.a.a.a.class_1. If we run the same import check against our control, we will see that this might be org.apache.commons.collections4.predicate, or org.apache.commons.collections4.transformer, or one of the other well-used classes in the unobfuscated version. Or maybe it's not. Who knows? You can see the counts don't match up even for the imports on _java.util.iterator_, so you can see that the characteristics of decompiled code will never be 100% consistent with the characteristics of the actual code. The point of counting import statements though is to get an idea of which of your essentially nameless classes might be playing a bigger role than others. Finally, another approach is to look for familiar elements and refactor the decompiled code with more meaningful or guess-based names as you read the code until the bigger picture starts to come together. You can open up the project in Eclipse, as I demonstrated in the Fernflower Basics video. Using the refactoring tools, you can programmatically rename class_1 to whatever you'd like, across the entire codebase. This in turn may yield insights into other areas of the code, and so on. Hopefully this video has given you some ideas about how to critically analyze the product of obfuscators like ProGuard. Perhaps it has also shown you a little more about the contravening purposes behind obfuscators and decompilers. This video is only a very small primer on the topic, and I hope to release more soon on topics that will build upon this material.